SwayamPrabha. Digital India. Educated India.
We would like to consider in this lecture relative displacement tensor, rotation tensor and strain tensor. We have already seen earlier how the strain tensor is defined. We would like to look into little more into the definition and show that the strain tensor is related to relative displacement tensor and rotation tensor. When you consider any component loaded, it will undergo displacements, and those displacements can include the rigid body displacements. It can also include the deformation. So, let us try to look into specifically into the case. We consider 3 dimensions and our axes are oriented as usual. Consider a body which is loaded. I am not showing the load here, that this is the body which is subjected to loading, and under the action of the loading it can move, it can rotate. So, therefore, it can have deformation also. It is moving in space and it has both rotation and deformation. So, if we confine our attention onto 2 points, although we are showing it to be these 2 points to be widely apart, but in fact, our interest is to consider these 2 points which are close by. So, these are the 2 points. Now, as it moves in the position that we have shown there, it might take up orientation which is given by P dash and Q dash. So, the point has moved in space like this. Let us consider that the distance between PQ can be indicated as a vector quantity, and let us say that this is the vector A, and this vector has components Ax in the x direction, Ay in the y direction and Az in the z direction. So, we can write A to be Iax plus Jay plus Kaz. Now, the displacement of any point on this body will make use of the function as usual, u for the x direction, v for the y direction and w for the z direction. This u, obviously it is going to be a function of the coordinate of the point. So, they are function of, so this u I, if we try to write in the form of a tensor, it is going to be a function of x, y, z. I takes up value 1, 2, 3, and in specific to be specific, I equal to 1 indicates u, and I equal to 2 indicates v, and I equal to 3 indicates w. I am sorry. Now, we would like to consider that the displacement of the point P, let us say that displacement of the point P is u0 and v is v0, w is w0. Now, we can write the displacement of the point Q, which is at a small distance apart from P. So, these are the displacements of the point P. Now, if we want to write the displacement of the point Q, we can write like this: u equal to u0 plus, we can write the Taylor series expansion for the functions ui. So, therefore, we will have delta u delta x ax plus delta u delta y ay plus delta u delta z az, that is the first order term. Then we are also going to get second order terms, which are nothing but delta u delta x square into ax plus delta u delta y square into ay plus delta u delta z square into az, and we can have higher order terms. So, we can write similar expressions for the other displacement. So, v can also be written. So, v is nothing but v0 plus delta v delta x ax plus delta v delta y ay plus delta v delta z az, plus we will have the second order terms and third order terms, and so on. Similarly, w can be written as w0 plus delta w delta x ax delta w delta y ay plus delta w delta z az plus the higher order terms. Now, if we neglect the second order terms, we can write the following. We can write u minus u0 V minus V0, W minus W0. This is nothing but in a compact form then we will have delta V delta x, delta V delta y, then delta W delta z, and the last row will have the derivatives of delta W delta x, delta W delta y, delta W delta z. So, therefore, this multiplied by the components of A, Ax, Ay, Az. This can be written in a compact form using tensor notation. We can make use of that ui minus ui 0 is equal to ui comma j multiplied by aj. So, this relationship let us indicate by 1. Herein this gives the this ui minus ui 0. Herein of course, we have assumed that I is taking up value 1 to 3 and j is taking up value also 1 to 3, and this I comma j, this indicates really all the derivatives. So, therefore, uij in is nothing but delta ui delta xj, and here we have all the 9 derivatives, and this is nothing but this expanded form which we have given earlier. So, this consists of all the 9 derivatives, and this is known as relative displacement tensor. Displacement this, since the displacements between the 2 points P and Q are changing by this much, this indicates really the change in the length. So, P moves in the x direction by u0 and Q moves by the distance u. So, therefore, in the x direction there is a change in the length u minus u0. So, the change in the length of the distance pq, if we indicate by delta ai, then we will have the components of the change are delta ax, delta ay and delta az. Then it is very easy to realize that this delta ai is nothing but ui minus ui 0. So, we can now write delta ai is equal to u I comma j multiplied by aj. This is known as affine transformation. Affine transformation. Now, the changes in the length in the x, y and z direction between the 2 points is given by this affine transformation. So, the initial components of the distance were ai and the final components of the distance are ai plus delta ai. Now, if we consider that the body displaced in such a way that there was no deformation, that means distance between P and Q remained unchanged, then we are going to get that the initial length square of the length between the 2 points are given by ax square plus ay square plus az square, that is the initial distance square, and that must be equal to ax plus delta ax square ay plus delta ay square plus az plus delta az square. Now, this will give us twice ax delta ax plus twice ay delta ay plus twice az delta az equal to 0, neglecting delta ai square terms. Now, we have the expression for delta x, delta ay and delta az. So, if we now consider and if we write them, it is going to give us ax into delta u delta x ax plus delta u delta y ay plus delta u delta z az plus ay into delta v delta ax delta v delta y ay plus delta v delta z az, plus we are going to get the third component plus az into delta w delta x into ax plus delta w delta y into ay plus delta W delta Z into AZ equal to 0. So, this if we now rearrange, it is going to be AX square delta U delta X plus AY square delta V delta Y plus AZ square delta W delta Z plus we are going to get AX into AY delta U delta Y plus delta V delta X plus AY AZ delta V delta Z plus delta W delta Y plus AZ into AX delta W delta X plus delta U delta Z equal to 0. Now, this relationship, if we call it 3, if we have AX, AY, AZ, they are always positive, and at the same time all these quantities are positive. So, therefore, if the left hand side is to be 0, this demands that the coefficient of all these terms have got to be 0. So, therefore, rigid body displacement condition. So, the body is going to move like a rigid body without deformation is going to be coefficient of all these terms are 0. So, therefore, it means that delta U delta X equal to 0, delta V delta Y equal to 0, delta W delta Z equal to 0, and then we have delta U delta Y plus delta V delta X equal to 0, delta V delta Z plus delta W delta Y equal to 0, and delta W delta X plus delta U delta Z equal to 0. So, these 6 conditions are the conditions for the rigid body displacement. Now, the relative displacement tensor, we can rearrange it. So, relative displacement tensor can be now rearranged like this, that Uij is equal to delta U delta X half delta U delta Y plus delta V delta X half delta U delta Z plus delta W delta X. Then we have half delta V delta X minus delta U delta Y delta V delta Y half delta V, delta Z. I am sorry, this is plus, I am sorry about that, this is plus, this is delta V, delta Z, delta W, delta Y, then we have half delta W, delta X plus delta U, delta Z, half delta W, delta Y plus delta V, delta Z and delta W, delta Z. So, this is the first part, and then we try to write plus 0, this is half delta U, delta Y minus delta V, delta X, half delta U, delta Z minus delta W, delta X, then this is half delta V, delta X minus delta U, delta Y, 0, half delta V, delta Z minus delta W, delta Y, then this one half delta U, delta Z minus this is delta W, delta W, delta X, I am sorry, delta W, delta X minus delta U, delta Z, half delta W, delta Y minus delta V, delta Z, 0. So, if we just write this, we get back, you can see that here we have added something, we have subtracted something, and then these two terms gives me back the original expression for Uij, and you can see that this is nothing but the strain tensor. This is the epsilon x, this is gamma xy, this is gamma xz, this is gamma yx, epsilon y, gamma yz, this is gamma zx, zy and epsilon z, and this is the strain tensor. So, therefore, this is the strain tensor epsilon ij, and this one is nothing but it is giving us the condition that it is rotation, this is the rotational tensor. So, therefore, this gives the rotation tensor ij. So, therefore, epsilon ij is the strain tensor and wij is the rotation tensor. So, you can see that the relative displacement tensor is nothing but sum of the Uij, relative displacement tensor is nothing but sum of the strain tensor and the rotation tensor. Epsilon ij will indicate this thing, I am sorry, this will indicate this thing as Wij. So, therefore, this is Wij. So, relative displacement tensor is sum of the strain tensor and the rotation tensor. Now, this can be written also in making use of the tensor relationship. Without detailing out, we can write it very in a compact form. Uij is nothing but half of Uij plus Uji plus half of Uij minus Uji. So, you get now the strain tensor. You are already familiar that this is the definition of the strain tensor, and this is the definition of the rotation tensor Wij. For pure rotation, I am sorry, for pure deformation will have no rotations, or for pure deformation Wij is equal to 0, and therefore, we have Uij is equal to Uji. Now, we would like to consider, having got this affine transformation, it is now possible to consider determination of the principal strains. So, we will now consider determination of principal strains. So, let us consider the determination of principal strains. Now, for pure deformation, we have delta Ai is equal to Uij half of Uij Uji into Aj, or we can write this thing as epsilon Ij into Aj, since Wij is equal to 0. Now, let us consider that this PQ that we considered is having it is aligned with the directions. So, the PQ is aligned with the directions with cosines Lm and n. Then in that case, we can write that Ax is equal to L into Ay is nothing but M into A, and Az is equal to N into A. Therefore, we can now write now that delta A I is equal to epsilon I j L j into A. Now, if PQ happens to be the principal strain direction, let PQ is a principal strain direction. So, if PQ is a principal direction, then we can write that the changes in length delta A change in length of element PQ, which is A, is nothing but it is going to be A into epsilon. So, we can now write that delta A I is nothing but it is we can write then delta A I to be L I into A into epsilon. So, we have already got delta A I equal to epsilon I j L j into A, and again we have them given by this one. So, if we consider that this relationship, let us say it is 1, this relationship is 2. Now, you can combine these two relations and you will get now that L j epsilon I j A minus L j delta I j A epsilon is equal to 0. This epsilon stands for principal strain, and I must also indicate that this A is the length of PQ. So, this particular relationship, it is very similar to what we have obtained in the case of principal stress. So, if we expand it, you will find that this is nothing but L1 into epsilon 11 plus L2 into epsilon 12 plus L3 epsilon 13 minus L1 into epsilon equal to 0, and this is epsilon L1 into epsilon 21 plus L2 into epsilon 22 plus L3 epsilon 23 minus L2 into epsilon equal to 0, and L1 epsilon 31 plus L2 epsilon 32 plus L3 epsilon 33 minus L3 epsilon 3 equal to 0. So, this is the expanded form of equation 3, let us indicate by 3 dash. Now, this involves equation which can be written in a form like this, that is compact form is 3, and you see that herein we have the L1, L2, L3 are the constants involved, unknown constants, and this is a homogeneous set of equation, right hand side is 0, and therefore, if it is to give us non-zero solutions, then in that case we must have determinant of the quantity epsilon ij minus delta ij epsilon must be equal to 0. So, this is the characteristic equation, and it is similar to, if you remember, in the case of stresses we had determinant of sigma ij minus delta ij minus sigma equal to 0 for stresses, for principal stresses. So, you have got a closely parallel relationship for the principal strains, and this relation is going to again be 4 can be expanded. It is going to be of a form epsilon cube minus j1 into epsilon square minus j2 into epsilon minus j3 equal to 0. This is a cubic equation involving the principal strain, and this j1, j2, j3 are called strain invariants. Similar to stress invariants, they are also strain invariants, and they will be obtainable from the strain components, and they will have closely parallel relationship. And with this you can find out the principal strains, 3 principal strains, and for each of the principal strains you can come back to this relationship 3 dash or 3 to get their corresponding directions. So, that is how you can determine the principal strains and their directions. Similarly, we can also consider the deviatoric strains. So, deviatoric strains in close parallel to deviatoric stress, we can have deviatoric strains, then we can have also hydrostatic strains, deviatoric strains, then hydrostatic, spherical, volumetric, strain, so we would like to now break the total strains into deviatoric and volumetric strains, and obviously we can have epsilon ij is equal to epsilon ij minus delta ij into epsilon m plus delta ij into epsilon m. This epsilon m is nothing but the mean strain, mean normal strains, and this is given by epsilon ii by 3, and therefore, this is nothing but epsilon x plus epsilon y plus epsilon z divided by 3. And we can represent epsilon ij in this form, epsilon ij dash plus delta ij epsilon m, wherein this is known as Deviatoric strain tensor, and this one is known as volumetric or hydrostatic strain tensor or spherical strain tensor. So, we will write this thing as hydrostatic strain tensor. There are certain typicalities which are associated with the strains, and we would like to look into the typicalities. These are known as strain compatibility conditions. We have already got the expressions for strains like epsilon x delta u delta x, epsilon y equal to delta v delta y, and then we have gamma xy is equal to delta u delta y plus delta v delta z. Now, we see that the three strain components are defined by the two displacement functions. Now, if we try to take the second derivative of this, if we differentiate this with respect to x and y separately, then what we have is delta 2 gamma xy delta x delta y. So, we will have this thing as delta cube u delta x delta y square plus delta 3 v, this should be x. So, this is delta y delta x square. Now, we can write this thing as delta 2 delta y square delta u delta x delta 2 delta x square delta v delta y. So, we have now this is nothing but epsilon x, this is epsilon y. So, we can write now delta 2 gamma xy delta x delta y is equal to delta 2 epsilon x delta y square delta 2 delta x square delta 2 epsilon y delta x square. So, therefore, this is the compatibility condition. You see that here we have the derivative x y, and this is the shear strain, and it is related to epsilon x, and the derivative is twice with respect to y, and here it is epsilon y, and the derivative is with respect to x. So, this is known as the compatibility condition, strain compatibility conditions. If we now consider the other combination, we can have gamma yz and the strains epsilon y and epsilon z. By close parallel, we can get delta 2 gamma yz, derivative should be with respect to y and z. This must be equal to delta 2 delta z square, it must be epsilon y delta 2 delta y square epsilon z. So, this is the second strain compatibility conditions in 3 dimensions, and the third one we can write now delta 2 gamma zx delta z delta x is equal to delta 2 delta z square epsilon x plus delta 2 epsilon z delta x square. So, these 3 relations are known as 3 compatibility conditions in 3 dimensions, and if we have 2 dimensions we are going to simply have this one strain compatibility conditions. It can be also shown that we will have another set of compatibility conditions. We will consider now these relationships are delta 2 epsilon x delta y delta z is equal to delta delta x minus delta gamma y z delta x plus delta gamma z x delta y plus delta gamma x y delta z. So, this is another strain compatibility condition, and the other 2 which are of the similar type delta 2 epsilon y delta x delta z delta delta x delta gamma y z delta x minus delta gamma z x delta y plus delta gamma x y delta z, and the last one delta 2 epsilon z delta x delta y is equal to delta delta z delta gamma y z delta x plus delta gamma z x delta y minus delta gamma x y delta z. These compatibility conditions can also be derived starting from these strains. So, what we find is that we have the strains satisfying some constraint conditions. They are 3 in this form and the other 3 are going to be in this form. Now, it will be good idea for you to see how this condition can be derived. Now, if we try to consider, so let us take as an example how to derive the compatibility condition which is shown here. So, therefore, prove delta z delta delta x minus delta gamma y z delta x delta gamma z x delta y plus delta gamma x y by delta z. In order to do this, what you have to do, you just take the expression for delta gamma xy, differentiate with respect to z, and then take the expression for delta zx, differentiate with respect to y, and similarly take the expression for gamma delta gamma yz and differentiate with respect to x, and then take this sum, and once you take that sum, you will find that you are going to have a relationship involving some expression which will finally lead to this left hand side. So, you try to take the expressions for the strains gamma xy, gamma zx, gamma yz separately and differentiate them as shown here, sum them up. Then once you differentiate this resultant expression with respect to x, you are going to get the left hand side.